Hello, I'm going to introduce the paper about decoupling cores, kernels, and operation systems. This paper presents Barrelfish DC, extension to the Barrelfish OS, which decouples physical cores from native OS kernel, and furthermore, the kernel itself from the rest of the OS and application state. In Barrelfish DC, native kernel code on any core can be quickly replaced. Kernel states move between cores and the cores added and removed from the system transparently to applications and OS processes, which continue to execute. Before I introduce the whole paper, I would like to show a short outline about this presentation. First, I will introduce motivation about trends in hardware and software. The next part is implementation on booting and shutting down cores dynamically. The rest of the paper, which about evaluation and conclusion, will be given by my partner. So, what's happening to the hardware? Today, we are mostly constrained by power consumption. This will bring us, for example, reconfigurable cores, which means we can dynamically change behavior. So this is what we already do today, like DVFS, which means dynamic voltage and frequency scheduling, and turbo boost, and also SMT. There's also some research technique like core fusion, which allow us to fill cores, multiple physical cores into simple, more powerful core, or split them up again. On the other hand, the future may have to do dark silicon, which means we can have many cores, but we cannot power them all at the same time. So what does it mean for us for adding and removing cores in the system? Well, we already do it today. For example, if cores fail or if reallocates cores to different machines. On the other hand, you may take cores out of service because we will not power them all at the same time. Also, there's heterogeneous cores. Heterogeneous cores in our machine giving us asymmetric performance. And for example, one such logical conclusion of this would be conservation cores. Now, we imagine we build an OS in a dark silicon area. So you have set heterogeneous cores, and you need to switch between the cores based on your workload. But you also need to power down and take cores out of service because you don't have the power to pack everything at the same time. So this is the current model today. The current runs as a single program in all cores, and every course run the same code, and it's hard to adapt like heterogeneous cores. So what happens if you move a core in such a system? Well, we have to go deep to the data structure to reflect this change. Typically, this requires global coordination, and also the data structures may be globally shared protected by locks. What happens if processor holding analogs? So there's a lot of issues there. And what's happening to software? In software, we usually need to adapt to different workloads in our OS. Now, general purpose kernels are very useful to adapt, but we still have to adapt to modify build, boot, and runtime. For example, to facilitate debugging with profiling and tracing. And sometimes application requirements are very strict, such as real-time support, and it's hard to adapt everything into general purpose kernel. Now, there are also research techniques that work by modifying or upgrading cores on the fly, as is the case, for example, Ksplice in Linux or K42 upgrade mechanism. So, we argue that a good architecture model dealing with dynamic cores or adapting to heterogeneous cores or changing software requirements is a multi-kernel model. In a multi-kernel model, each core runs separate kernel programs, and the state is currently in per-core state into what we call OS node. Now we still have to run applications on the top of that, and applications may share state between cores. Therefore, we replicate the state between cores using asymmetric message passing. So, however, a multi-kernel model is not enough dealing with dynamic cores. So we still need to deal with OS node. So I'm going to so we use as a basis with Barrelfish is an implementation of multi-kernels, and we add some features to multi to Barrelfish that we call the Barrelfish DC, which I mentioned at the beginning. Treat cores as much as possible as pluggable device. So we will next of how we booting a core dynamically with boot drivers and how we shut down a core in system. We use the technique that externalize kernel state that allow us to decouple cores, kernels, and operation systems. After introduce the rest of the implementation, we should mention that I should mention that the paper focused entirely on mechanisms in this paper. So don't address scheduling and the policy for kernel replacement, core power management, or application migration. Note also that this paper main motivation in Barrelfish DC is adapting the OS for performance and flexibility. So this paper doesn't consider fault tolerance and isolation. First is about booting a new core. Bring a new core online is a question of turning on, updating this table, and creating per core state when needed. Previous version of Barrelfish also adapted this approach and booting all cores during system initialization, though there has been experimental work on dynamic booting of heterogeneous cores. Barrelfish DC targets a broader hardware landscape with complex machine comprising potentially heterogeneous cores. Furthermore, since Barrelfish DC runs a different kernel instance on each core, there's no reason why the same kernel code should run everywhere. So we need an OS representation of a core on machine which abstracts the hardware dependent mechanism for bring the core up and down. Therefore, Barrelfish DC introduced the concept of a boot driver, which is the piece of code running in a home core, which manages a target core and encapsulates the hardware functionally to boot, suspend, resume, and power down the later. Currently, boot driver runs as a process, but closely resemble a device driver and could equally run as software objects within another process. A new core is brought online as this 5-step. First is the new core is detected by some platform-specifically mechanisms, and its appearance registers with the device management subsystem. The second step is Barrelfish DC select and start appropriate boot driver for a new core. Barrelfish DC selects a kernel binary and argument for a new core, and directs the boot driver to boot the kernel on the core. The first step is the boot driver loads and relocates the kernel and executes the hardware protocol to start a new core. The new kernel initializes and uses existing Barrelfish protocol for integrating into running OS. Booting a core in Barrelfish DC only involves two processes: the booting driver on the home core and the kernel on the target core. For this reason, we require no global locks or other synchronizations in the systems, and the performance of this operation is not impacted by loads on other cores. And next is about shutting down a core. It's much harder than booting a core because we need to deal with poor core state, like we need to take more space for scheduler queues and memory pool, also the page tables. It means we need more time and energy. However, we want to remove the core as fast as possible. The general approach that follows, like Chalimans, is getting state out of the way quickly and dismantle it later or lazily. So how did it work in our OS? First, we close them away, and we are able to capture this OS or all per core state, and we move it to a different core. Now, we add an OS scheduler into kernel that is able to dispatch the different OS node. And we call this core one OS node removed to a kernel that already have an OS node, temporarily parking OS node. And we can already notice here, this approach is highly scalable, as we only involve two cores in process right now. We don't need to normally coordinate it in this system. So what happened next? We can either move back to previous cores or to move it somewhere else. And we should pay attention. What is the OS node? And how do we capture this OS node? This is typically not clear in OS. Per core state is not explicitly defined and typically have many different states data structure. So in this paper, they use partitioned capability system to explicitly capture OS nodes, meaning entire per core state in a single data structure. First, I want to introduce about the frame and C code in the partition capabilities. Capabilities are typed to reflect what the memory is used for. A frame capability refers to memory that the holder can map into their address space. C node capability refers to memory that is used to store the bit representations of capabilities themselves. So this captures all accessing information and memory allocations about applications. So all per core states in the kernel are now be accessed to this structure or reconstructed from the capabilities trees. We still need to be able to reach this structure and pass it around our system. Therefore, we add a KCB or kernel control block. KCB combines some states that don't need to persist across the kernel start. KCB is also a capability itself. It means we now have a representative handle in system to move entire per core state or out. So this method of state externalization and dynamic core booting is much more general mechanisms because we are now able to move per core states around internally in our system, and we can also replace the kernel dynamically on OS node. Also, I want to talk about how to deal with the interrupts. In general, interrupts distinguished into three types of interrupting in systems like handle local to cores and the CPU driver like timer. Also the interprocessor interrupts which set between OS node, and also the device interrupt. So what happens if we have a device interrupt? A device that runs on some cores and is migrated to a different core. Right now, we essentially marks all the interrupts and on the core, and then we have to register the interrupts on the device driver. So we typically doing this process is sometimes happening between you have to go and check again if something happened into device, or you can pull the device while doing this shift. Okay, welcome to my partner to introduce the rest of the paper. Thank you.